Have you ever been on a quest for that perfect melon? We tap it, push on the ends, listen to it, shake it, smell it, and all kinds of things. Why do we do this? We do it because we try to find out what's on the inside. Is it ripe fruit or something not good or overripe? We try to use our senses to gain as much information as possible about this piece of fruit to determine what it's like on the inside. And hopefully we are successful. Yum! One of the first questions that gets asked when people start learning about the 5 layers of the earth is, how do people know what the interior layers of the earth are like if we can't get there to see? This answer is very similar to searching for the perfect piece of fruit and is the subject of this lesson. While we can't pick up the earth and shake it, and smelling it probably wouldn't help us much, tapping on the earth and listening to the sounds it makes does have some possibility. We can do this by exploring earthquakes and volcanoes. We hear about them and the destruction that they can cause, like Mount St. Helens, Vesuvius, Pinatubo. In a volcano, melted rock called magma breaks through the crust and begins to pile up on the surface, forming any one of a variety of cones. Volcanoes can erupt in one of 2 ways, either suddenly and violently like Mount St. Helens or Pinatubo, or slowly and gradually like the Hawaiian volcanoes. One of the factors that determines whether they explode or not is the amount of silica in the magma. The more silica present, the more solid it can become, plugging up the chambers under the ground. Pressure then builds up, causing the catastrophic eruptions seen in Mount St. Helens, Pinatubo, or Krakatoa. Magma with relatively little silica is much more fluid and will flow more like water, as the volcanoes in Hawaii do. Either way, scientists can get a glimpse of the contents of the layers under the Earth's crust by studying the debris that erupts from these landforms. Another theory about why some volcanoes erupt violently and others do not gives some understanding about the content of the gases in the Earth. Sometimes the magma rising to the surface of the Earth happens quite fast. When it does, the gas bubbles in the magma begin to expand as the pressure decreases. When the magma reaches the surface, there is a large release of the pent-up gases, causing the volcano to erupt, much like opening a soft drink that has been shaken. In an eruption that is non-explosive, scientists think most of the gas has had a chance to be released, as the magma has risen to the surface more slowly. This leaves little gas to be released, and just the magma is emitted from the Earth. Earthquakes provide a completely different way to view the Earth's interior. Almost all the data gathered about the deeper regions of the Earth's interior comes from the travel of earthquake waves through the Earth. When an earthquake occurs, it produces several kinds of waves. S waves and P waves are the waves that are most often analyzed to provide a glimpse into the Earth's interior. S waves are known as shear waves, and are transverse waves, meaning they shift perpendicular to the direction the wave travels. This would be like shaking the end of a slinky up and down and seeing the waves travel along it. These waves travel only through solids, so scientists can track where these types of waves show up and how they are absent in other places. From this information, they can figure out which layers of the Earth are solid and which are liquid. Another type of wave is a compression wave, and are also known as P waves, and are the faster of the 2 types. P waves are waves that travel through the layers of the Earth by compressing the matter they travel through. This is similar to how sound travels through the air, and would be like taking the end of the stretched slinky and pushing it towards the other end. The resulting wave is a compression wave that travels through the spring. Compression waves travel between 5 and 8 kilometers per second, or 3 to 5 miles per second. They are able to travel through solids and liquids along the surface and through the Earth's interior. These waves actually can travel to the opposite side of the Earth by traveling through the Earth's layers and be detected by instruments there. Scientists measure how long it takes to reach different places around the Earth, and since these waves travel at different speeds through solids and liquids, the structure of the layers can be determined by analyzing the arrival time and location. Another interesting feature of these waves and their travel through the Earth is the presence of a shadow zone, which is an area of the Earth between 103 and 142 degrees from the earthquake's focus, where no waves can be detected. As the P waves strike the boundaries of different layers in the Earth, the waves are bent or refracted since they travel at different speeds through different substances. This is precisely the effect that scientists use to determine the structure of the Earth's interior layers. According to the United States Geological Survey, or USGS, this information, the slowing of the P waves and the lack of S waves, was the main piece of evidence that allowed scientists to determine the outer core of the Earth was liquid. They also used the size of the shadow zone to deduce the diameter of the core. So, by analyzing where and when these earthquake waves appeared at points around the Earth, scientists have developed a model of the structure of the Earth's interior. Since we cannot directly observe the interior of the Earth, scientists need to rely on other data to develop a model of the Earth's interior. They do this by relying on information from volcanoes and earthquakes. Data about the composition of some of the Earth's layers is gathered by studying the debris that is emitted from a volcano. Its explosivity is also a measure of the gas content of the magma. Scientists use S waves, or shear waves, and P waves, or compression or pressure waves, that result from earthquakes to determine the size of layers and also to tell if they are solid or liquid. Since only P waves can pass through liquids, and they are refracted or bent as they pass from one layer to another, a shadow zone, an area where no waves appear, forms, giving evidence of the size of the core. All of this data is combined to allow a glimpse into the structure of our planet Earth.